So this year, before September, a star in the constellation of Corona Borealis will explode, and in the Northern Hemisphere, we'll be able to see it with the unaided eye. The star is T Corona Borealis, a white dwarf star 3,000 light-years away from our solar system. It will turn into a nova, which we'll discuss a bit later, in spring or summer. Even though this occurrence is predictable, happening every 80 years, it's still a once-in-a-lifetime event, if you're human. T Corona Borealis is not your regular star. It's actually a binary, two stars orbiting each other. This pair, though, is incredibly special. Occasionally, the stars increase their brightness to such an extent that they become visible on Earth. The white dwarf star is the more massive one of the two. But the most shocking thing about it is that it might pack the same mass as the Sun into a volume only as large as Earth. The companion star, an aging red giant, has already expanded so much that it's dumping its material onto the white dwarf. So it's time for another explosion for these two. It's going to take the star's brightness from magnitude 11 to magnitude 2. You see, in astronomy, magnitude is used to measure the brightness of a star or another celestial object. The brighter it is, the lower the number assigned as a magnitude is. It's like golf, low scores, you know. In our case, it means that we'll be able to see the star with the unaided eye, even in light-polluted skies. Now, we can only see the binary with binoculars in a completely dark sky. After the outburst, T Corona Borealis will remain the brightest star in the constellation of Corona Borealis for a few days before gradually dimming. Now, this event shouldn't be confused with a supernova. In a supernova, a star's core collapses, which leads to its complete destruction. It can only happen to a star 8 times the mass of the Sun. Instead of disappearing in a blinding flash of light forever, T Corona Borealis will experience a nova, an explosion on its surface, flinging matter into space but not ruining the star itself. Such recurrent novas happen at regular intervals. T Corona Borealis was known to astronomers from the past as the Blaze Star. Last time it exploded in 1866 and 1946. Astronomers from NASA believe it's going to do it again before September this year. The constellation of Corona Borealis, also known as the Northern Crown, is one of the most beautiful out there. It's a curved semicircle of 7 stars, which is easy to find in April. You should go outside 2 hours after dark and look to the east-northeast. Once you find the Big Dipper, use the curve of its handle to go to Arcturus, finding the bright star in the Buddhist constellation due east. If you go diagonally down to the east-northeast horizon, you'll spot Corona Borealis. Now, if you want to observe the brightening of T Corona Borealis, it might be better if you get acquainted with the region and the stars of the constellation it's in. Once the event begins, you'll be able to compare its brightness against the other stars and observe the thing without using any fancy cameras. Now, a nova is a short-lived sudden explosion, involving a compact star as large as Earth or a bit bigger. The outburst comes from a white dwarf circling remarkably close to a regular star, so close that a stream of gas flows between them. This gas starts piling up until it creates a layer on the white dwarf's surface, and then it reaches a point where it detonates in a runaway thermonuclear explosion. According to astronomers, around 50 nova happen every year in our galaxy, but not all of them are noticed. NASA's Fermi Gamma Ray Space Telescope has observed several nova that occurred not far on the scale of the universe. They found out that each blast produces gamma rays. Those are the most energetic forms of light. Researchers also think that these gamma rays result from collisions among numerous shock waves, racing from the explosion site in a quickly expanding shell of debris. Now, after we've talked about novae, it's time to discuss something much more dramatic: supernovae. It's the largest explosion humans have ever seen. Each blast is a super powerful burst of a star. One kind of supernova is caused by the last hurrah of an extinguishing massive star. It happens to stars at least 5 times the mass of our Sun. Once they near the end of their lives, they go out with a ginormous bang. Huge stars burn incredible amounts of nuclear fuel at their core, producing tons of energy. It makes their centers immensely hot. Heat generates pressure, and this pressure keeps such stars from collapsing. But any star is in balance between two opposite forces. Its gravity attempts to squeeze the star into a teeny tiny ball, and the nuclear fuel burning at the core of the star produces powerful outward pressure. Now, when a giant star is running out of fuel, it starts cooling off. Its pressure drops and gravity wins. The star collapses. An enormous object that is millions of times the mass of Earth collapses within 15 seconds. No wonder this brisk process produces enormous shockwaves. It makes the outer layers of the star explode. Eventually, an incredibly dense core is all that is left behind, besides a growing cloud of hot gas called a nebula. A black hole, the densest object in the universe, is the result of a supernova of a star around 10 times as massive as our Sun. Also, there's another type of supernova. It usually happens in systems where two stars orbit each other, and at least one of these stars is a white dwarf the size of our planet. If such a star collides with another, or pulls too much matter from its neighbor, it can explode into a supernova. Also, supernovae are often so bright they can outshine the combined light of entire galaxies for several days or even months. Supernovae aren't common. Astronomers think just a few of them occur within the century in galaxies like our home Milky Way. But since the universe contains an enormous number of galaxies, we can observe a few hundred supernovae every year outside our galaxy. Unfortunately, space dust blocks our view of most supernovae happening within the Milky Way. Betelgeuse, a late-stage red giant, exploded in 2019, but it wasn't the event we expected to see. This star is found in the constellation of Orion and is huge, so big that if we moved it to the center of our solar system, its outer edge would go way beyond the orbit of Jupiter. When Betelgeuse eventually nears its end, it will explode in a stunningly bright supernova visible on Earth even during the day. This explosion could happen as soon as tomorrow or as far-flung as hundreds of thousands of years from now, so don't hold your breath. But then, what was it in 2019? Astronomers noticed that the star was dimming. They decided it was the initial stages of the grand show. But instead, Betelgeuse went back to normal over the course of the next few months. Further analysis revealed that the star hadn't dimmed. It just looked like that because we had been observing it through a cloud of stellar debris. At the same time, the amount of light in the photosphere of Betelgeuse ramped up. It was like a massive explosion of material from the surface of the star. Events like this occur on the Sun all the time, especially when our star's activity is high. Bits of the Sun's surface get tangled up and cast off. That's what we call coronal mass ejections. They don't harm our planet, but they can mess with satellites and electrical equipment. Now, getting back to Betelgeuse, we've never seen such a huge mass ejection on the surface of a star before. It's a new phenomenon which we can observe directly and even see surface details with the help of the Hubble telescope. Astronomers say we're watching stellar evolution as it happens for the first time.
Usually, when we look at the photos of astronauts in space, we can see that they're sort of attached to the spacecraft. But there was one brave astronaut who took a wild step into the great unknown without any safety line connecting him to the shuttle. This brave man was Bruce McCandless, and he did that stunt back in 1984. How did he come back, you may ask? He did this cool trick using a nitrogen jetpack, which NASA called the Manned Maneuvering Unit. At first, he tried out some test maneuvers in the Challenger's payload bay, and only after he made sure it was all right did McCandless decide to go for it and glide a staggering 320 feet away from the shuttle. A bit of sad stats here. Out of the 430 people who have made the leap into space, 18 have sadly lost their lives, which gives us a fatality rate of just over 4%. With these numbers, it's safe to say that space shuttles are the least safe means of transport out there. Duh. Alright, let's make it a tad brighter. If we crunch the numbers a bit better, we can get a smaller percentage. But how? Well, 4% is a bit misleading because when we count, we take all the space flights. However, some people flew several times, which reduced the probability. With over 600 seats filled across 113 shuttle flights, The true fatality rate for shuttle missions is actually closer to 2%. Let's test your general knowledge now, shall we? So, what was the first living thing ever sent to space? If your answer is a monkey, you aren't right. Those who said dogs, sorry you guys, but it's not correct either. On the 9th of July, 1946, fruit flies became the first living creatures to make it to space during a suborbital V-2 rocket flight. Then, on the 20th of February, 1947, these little guys safely returned from their journey, opening the door for future human space exploration. Before, we sent to space mammals like the rhesus monkey, Albert II, in 1949, or the famous space dogs. Scientists spent a lot of time studying fruit flies to see how they reacted to radiation and the conditions of space travel. Researchers started using fruit flies for experiments back in the 1910s. Guess why? Because we humans share a lot of genes with these yucky pests. Imagine hearing some creepy music all of a sudden, when there's nothing but darkness around you and nobody is there to help you. Right, now imagine how elevated this experience was for astronauts who heard some creepy music in their space shuttle. Months before the moon landing, Apollo 10 astronauts were orbiting the moon, testing equipment, when they heard strange audio noises. Astronaut Eugene Cernan noted the eerie sounds, joking they were like weird music. At that moment, the astronauts didn't have contact with mission control. They were over the moon's dark side. Although the noises resembled something from a sci-fi film, NASA downplayed them as they were focused on the astronauts' mental health. Despite years of speculation, the source of the sounds remains unknown, with theories ranging from radio interference to charged particle activity. Cernan later remarked that they didn't take it seriously and didn't report it after the mission. Chances are, we've already received messages from new friends from other galaxies, but we just failed to understand them. In August 1977, some astronomers using the Big Ear radio telescope at Ohio University picked up a strange narrow-band radio signal from the constellation Sagittarius that lasted for 72 seconds. The signal buzzed at a frequency of 1,420 megahertz, which is significant because it matches the natural emissions from hydrogen. This frequency had been flagged by scientists almost 2 decades earlier as a likely choice for extraterrestrial civilizations trying to reach out to us. They dubbed it the WOW signal after one of the astronomers wrote "WOW" on their printout. We've never heard that signal again, and no one has been able to explain its origins satisfactorily. After spending about a month in space, astronauts start losing quite a lot of skin from the bottoms of their feet, especially those tough calluses they've built up over time. One astronaut even called mission control in a bit of a panic when he noticed a chunk of his heel drifting off in zero gravity. But no worries, as the old calluses peel away, new ones spring up from the tops of their feet. They need that grip to hold on to all the restraints, kind of like airborne trapeze artists. Going number 1 and seeing blood is as scary as it sounds, and yes, in the weightlessness of space, blood doesn't settle in the lower body in the same way it does on Earth. This can lead to some alarming situations on board. Natural urges are universal, regardless of location. There are 2 main reasons why astronauts are unable to use traditional toilets in space. First, water is an extremely valuable resource aboard a spacecraft. Second, there's no gravitational flow of water in space. The drinkable water on a space station is contained in pouches and is used accordingly. In a weightless environment, a specialized device with suction and disposable bags is used for waste collection, with the storage being replaced every 10 days. Additionally, spacecraft are equipped with complex systems designed to recycle and filter liquid waste, converting it back into usable water for the astronauts' daily needs. As if that wasn't enough, spending an extended period floating around in space brings another challenge. The body may lose its bursa sacs, those handy little cushions that sit between our hip joints. While this may not pose an immediate issue in the zero-gravity environment, returning to solid ground can turn the simple act of sitting down whether in a chair or on a toilet, into a real struggle. The fluid shifts that contribute to blood-related issues don't stop there. They can also wreak havoc on astronauts' sinuses, creating a constant feeling of congestion. It feels like living in a stuffy room all the time, where relief seems just out of reach. Thus, the challenges of long-term space travel add up, making the experience as daunting as it is thrilling. Another challenge astronauts run into is vision loss, also known as ocular syndrome, which sounds all sciencey. While the exact cause is still a bit of a mystery, it's thought that extra pressure on the brain can mess with both the retinas and optic nerves. And here's a fun fact: it mostly affects guys. By the way, you might assume that shutting your eyes in space means it's pitch black, but that's not the case. Because of high levels of radiation, astronauts can still see bright lights when they zip through certain parts of their orbit. It's a pretty strange phenomenon that keeps them on their toes, even with their eyes closed. Switching gears, let's talk about bone health in space. It turns out that being weightless can really take a toll on astronauts' bones. Like, they can lose up to 2% of their bone mass every month, which is pretty wild. But the good news? They've come up with new exercise routines that help fight off that bone loss. So, while space travel definitely has its challenges, researchers are working hard to keep astronauts in tip-top shape as they explore the universe. The Big Crunch is a cool theory about how the universe might end, and it's basically the opposite of the Big Bang. So, imagine the universe expanding for ages, but then it hits the brakes and starts collapsing in on itself, maybe even forming a huge black hole. Scientists are looking into this by checking out the universe's density. If it's too dense, such a collapse might really happen. At first, people thought that gravity would eventually take over and stop the expansion from the Big Bang. But then we found this mysterious thing called dark energy, which is actually speeding up the universe's expansion. Because of that, it seems like the Big Crunch is pretty unlikely. Right now, the evidence shows that dark energy is here to stay, so the universe will just keep on expanding forever. Locating the North Star is quite easy on a clear night. The only thing you need to do is find the Big Dipper. Those two stars on the end of the Dipper's cup point the way to the North Star. See? It's the tip of the handle of the Little Dipper, or the tail of the Little Bear. It's in the constellation Ursa Minor, over there. People have been watching the North Star for centuries. This bright star is also known as Polaris. It's situated almost directly over our planet's North Pole, which makes it a great landmark for a traveler without a compass, or a GPS on their smartphone. It's also Earth's closest Cepheid. That's what we call a star that pulses regularly in brightness and diameter. Polaris is also part of a binary system of two stars. It's got a dimmer sister. It's known as Polaris B. You can actually see it circling the North Stars from Earth. But the more astronomers watch Polaris, the less they understand. The problem is, no one can agree on how big or distant the star is. Scientists have several ways to estimate the mass, age, and distance of a star like Polaris. One method is called the stellar evolution method. After studying the brightness, color, and rate of pulsation of a star, experts use this data to figure out how big or bright it is, as well as what stage of life it's in. Once these details are clear, it's not hard to find out how far a star actually is. It's simple math once you know the luminosity of a star in real life and how dim it looks from our planet. Such models are especially precise for stars like Polaris because the rate of their pulsing is directly related to their brightness. This makes it easy to figure out the distance to any of those stars. Astronomers trust this method so much that Cepheids have become an important tool for measuring distances all across the universe. At the same time, there are other ways to study the North Star, and they don't agree with the stellar evolution models. Polaris is a so-called astrometric binary. It means you can see its companion going around it. It looks as if a circle is being drawn around the bigger star. To complete one orbit, the smaller star needs around 26 years. Even though astronomers haven't made detailed observations of Polaris B's full circuit, they've seen enough to know what its orbit looks like. Using this information, one can apply Newton's laws of gravity to calculate the masses of the two stars. Combined with the Hubble Space Telescope's new measurements, these calculations lead to very precise numbers. Polaris is supposed to be around 3.45 times the mass of the Sun, but that's much less than the mass you get from stellar evolution models. They suggest a value of almost 7 times the mass of the Sun. But there's another reason why this star system is weird. After calculating the ages of the stars, researchers concluded that Polaris B is much older than its bigger sibling, but it's extremely unusual for a binary system. Normally, both stars are of the same age. One explanation might be that at least one of the measurements is simply wrong. After all, Polaris is a difficult star to study. Since it's positioned above our planet's North Pole, it's outside the field of view of most telescopes. As for those telescopes that do have the needed equipment for measuring the star's properties precisely, they're typically used for studying much more distant and fainter stars. Polaris is simply too bright for such instruments. It blinds them. There's a theory that the main star of the Polaris system was once two stars, but they collided a few million years ago. Such a binary collision could rejuvenate stars by pulling in extra material and making the stars look as if they went through the fountain of youth. It would also explain some other oddities, since stars that appear as a result of binary collisions don't fit stellar evolution models. Unfortunately, so far, none of the theories have been confirmed. The North Star is actually a big deal. Earth is spinning non-stop, which causes the sun to rise and set and stars to travel across the sky. Our planet is also tilted. That's why we have seasons. If we drew a line through the axis Earth spins around and extended it over 300 light-years past the North Pole, at the end of that imaginary line, there would be the North Star. It stays almost exactly at the same spot in the sky at all times, and always points the way north. It's really important for navigation. People heavily relied on it in the days before GPS. If you were standing on the equator, Polaris would be right at the horizon. At the North Pole, it would seem to be right over your head. In other words, using the star's height in the sky, you can not only figure out the needed direction, but also understand where you are on Earth. Curiously, there's no South Star. There isn't a bright enough star right above the South Pole, but one day we might get such a star. When you spin a top on the table, its end moves in a circle. We know this phenomenon as precession. Earth behaves in the same way, and the North and South poles won't always point towards the same spots in the sky. In the next 26,000 years, it may cause the North Star to change from Polaris to a few other stars and back again. One day, the title of the North Star will go to Vega. It's the 5th brightest star in the night sky and the 2nd brightest in the northern celestial hemisphere. Vega has another name, Alpha Lyrae. That's because it's the main star of the Lyra constellation. Vega has been one of the most crucial stars to people since ancient times. It's very bright and blue, hence very recognizable. Vega was the North Star several thousand years ago, and it'll regain this status in 12,000 years or so. This star is located a mere 25 light-years from Earth. It's just 450 million years old, which makes it way younger than our own 4.6 billion-year-old star system. Astronomers study Vega to learn more about star systems in the early stages of their formation. Vega is almost directly overhead at mid-northern latitudes on a summer night. It hides behind the horizon for only 7 hours a day. You can see it on any night of the year. If you travel farther south, you'll find out that Vega lies below the horizon for longer periods of time. But in Alaska, northern Canada, and some parts of Europe, Vega never sets. Vega's blue-white light is bright enough to be featured a lot in ancient cultures, from the Chinese to the Polynesians to the Hindus. Vega's name can also be translated as falling or swooping. This is a reference to the times when people regarded this constellation as a swooping vulture, not a Lyre. Vega was also the first star to get photographed, other than the Sun, of course. To do it, astronomers at Harvard College Observatory used a 15-inch refractor, and it happened again in 1850. Around 2 decades later, an amateur astronomer broke down Vega's light to reveal various elements making up the star. In 2006, thanks to telescopic observations, scientists found out that Vega was whipping around so fast that its poles were several thousand degrees warmer than its equator. The star rotates every 12.5 hours and is at 90% of its critical rotation speed. That's the velocity at which an object can tear itself apart. In 2013, researchers announced that they had discovered an asteroid belt around Vega. It means there might be planets somewhere out there among space rocks. There are 2 areas, an outer region that contains icy asteroids and an inner region with warmer space rocks. Scientists can examine bright stars like Vega using NASA's mission called TESS, which stands for Transiting Exoplanet Survey Satellite. It was launched in 2018 to conduct an all-sky survey. The main goal of this mission is to search for exoplanets, but the satellite can also look for star variability. By examining such stars as Vega, TESS can help scientists learn more about the early stages of star evolution. Doctor, I can't understand what's going on. I feel dizzy and, how do I say it? I'm tilting. It didn't happen overnight. Like, I didn't wake up and couldn't stand straight. No, one day, I felt that my axis had shifted by 1 inch. Another day, it was 2 inches. And once, you won't believe it was 31.5 inches. That's alarming. What if I accidentally turned upside down and all my inhabitants fall off my surface? Ah, dear Earth. We ran some tests and are ready to explain an unfortunate combination of factors that has affected your axis. The last one will perhaps be the most unexpected and upsetting. It all started back in March 2011, when a devastating magnitude 9 earthquake struck off the coast of Japan. It was so powerful that not only did it shift Earth's axis, but it also shortened the length of the day. This earthquake displaced our planet's axis by approximately 6.5 inches and may have moved Japan's main island by about 8 feet. Like other similarly massive earthquakes, it also altered Earth's rotation speed. To make it easier, let's compare it to a spinning ice skater. When a skater pulls their arms close to their body, they spin faster by concentrating their mass near the axis of rotation. Something similar happens during the most powerful earthquakes. They shift Earth's mass closer to its rotational axis, causing it to spin faster and shortening the day length. The calculations showed that the Japanese earthquake sped up Earth's rotation by about 1.8 microseconds, which is about 1.8 millionths of a second. Not a big deal, but at the end of the day, every nanosecond counts. For comparison, the infamous Indonesian earthquake shortened the length of a day by 2.68 microseconds. It struck on December 26, 2004, at 0:58 UTC. The epicenter lay off the western coast of northern Sumatra, Indonesia. This powerful undersea earthquake triggered devastating tsunamis that swept across the Indian Ocean, causing widespread destruction and immense loss of life in countries like Indonesia, Sri Lanka, India, and Thailand. Even coastal areas as far as East Africa had severe damage. The Earth's magnitude, initially recorded at 9.0 on the Richter scale, was later adjusted to between 9.1 and 9.3, making it the most powerful earthquake ever recorded in Asia. The faulting, that's when Earth's crust completely breaks and its parts slide past each other, lasted between 500 and 600 seconds, and it was the longest duration ever observed. The immense force of the quake caused the entire planet to vibrate by at least half an inch and triggered other earthquakes as far away as Alaska. All that immense energy the earthquake released caused subtle but quite measurable changes to Earth. The shift in mass slightly changed the planet's rotation, shortening the day. It also caused a small wobble in Earth's axis from 1 to 2.4 inches toward 145 degree east longitude. So, When it comes to changes in Earth's rotation speed and axis, it's all about the redistribution of mass. This can happen naturally, through disasters, but human activities can also trigger it. Take the Three Gorges Dam, for instance. This massive structure across the Yangtze River in China's Hubei province may seem to be an engineering triumph, but it's pretty ambiguous. Finished in 2012 after nearly 20 years, this massive dam is 7,660 feet long and 607 feet high. And yes, it is so big that it can affect the way our planet spins. Its reservoir is capable of holding 9.5 cubic miles of water, has enough mass to slightly alter the Earth's rotational inertia, slightly slowing the planet's rotation. According to NASA, the Three Gorges Dam reservoir could shift Earth's pole position by almost 1 inch and increase the length of a day by 0.06 microseconds. Dams aren't the only worry. If polar ice melts, water rushes into the oceans, hiking up sea levels, especially near the equator. This mass shift slows Earth's spin way more than dams do. You won't feel it day to day, but it can affect ultra-precise equipment, such as atomic clocks. To fix this, scientists suggested a negative leap second, making a minute 59 seconds, to balance Earth's spin changes. Okay, so you're thinking you've got nothing to do with all those tilts. You don't build dams, right? Bad news. If you take regular showers, you're part of it too. Every time you turn on the tap, you're affecting Earth's tilt just a tiny bit. Thing is, our planet is always shifting and adapting, so even small actions like using water can influence its orientation. Over the past 2 decades, groundwater pumping has caused the Earth's tilt to shift by 31.5 inches. This water redistribution is equal to about 0.24 inches of sea level rise. It turns out that among climate-related causes, groundwater redistribution has the largest impact on the drift of Earth's rotational pull. But what is groundwater? It's the water stored beneath the Earth's surface, filling the spaces in soil, sand, and rock. It comes from rain and other precipitation that seeps into the ground, collecting in underground reservoirs, aquifers. Unlike rivers and lakes, groundwater stays below the surface, acting like a natural water reserve. Thanks to it, we have a steady supply even during dry periods. Many people, especially in rural areas, rely on groundwater as their main source of drinking water. Farmers use it to irrigate crops, while industries depend on it for manufacturing and cooling systems. It sounds pretty harmless, doesn't it? How can something so useful cause our planet to shift? Well, a study covering data from 1993 to 2010 revealed that we've pumped about 2,150 gigatons of groundwater in that time. And this large-scale water removal has shifted the Earth's tilt and rotation. After we use groundwater, much of it eventually flows into the oceans, contributing to rising sea levels. In areas like Western North America and Northwestern India, people use a lot of groundwater, and it may have a connection to these shifts. Yikes, let's face it. All these findings are rather disturbing. But understanding the impact of groundwater use is already a huge step in the right direction. Hey, I'm not done yet. This tilting issue isn't just about stuff happening on Earth. We also need to look at space. We've talked a lot about water, right? Well, you know that the moon has a big role in that. Its gravity is super important for forming tides and all that. So one more thing that affects our planet a lot is the gradual movement of the moon away from Earth. These two bodies interact gravitationally, which makes Earth's rotation slow over time, even though significant events like earthquakes occasionally speed it up temporarily. How did we figure it out? Glad you asked. Once, someone paid attention to ancient corals. After analyzing them, scientists realized that Earth had once rotated much faster. The thing is, Corals grow by laying down thin layers of calcium carbonate. They do it daily, and variations reflect seasonal changes. By counting these layers, scientists have calculated the number of days in a year millions of years ago. They found that Earth had about 420 days per year 444 to 419 million years ago. But over time, the Moon's influence had caused Earth's rotation to slow. And now we only have 365 days in a year. I feel robbed, you know? At the moment, the Moon is moving 1.5 inches away from Earth each year. That's about the same speed at which your fingernails grow. Astronomers have figured it out with the help of special mirrors placed on the Moon during the Apollo missions. For over 50 years, researchers have been sending laser beams to these mirrors and measuring the time it took for the light to bounce back. In any case, dear Earth, at the moment, your condition isn't critical. As for your inhabitants, they won't fall off your surface. All thanks to your gravity, pulling them toward your center. Just don't switch it off, and everything's gonna be fine.
The two Voyager spacecraft have had a great track record. They took photos of such planets as Jupiter, Saturn, and Neptune, and then just kept going, beyond the outer edge of the solar system. At the moment, Voyager 1 is more than 15 billion miles away from our planet, and is still transmitting. Surprisingly, it takes only 22 hours for the signal to travel from the spacecraft to Earth. But how is it even possible to send signals for such unimaginable distances, considering that the satellite's processor is weaker than the processor from car keys? Both Voyager spacecraft use 23-watt radios. This is higher than the 3 watts a regular phone uses, but it's still considered to be a low-power transmitter. Interestingly, because of the ginormous distance, the phone's 3-watt signal, traveling around 100 miles on Earth, is billions of billions times more powerful than a 23-watt signal coming from Voyager. By the way, large radio stations on Earth transmit at tens of thousands of watts. This puzzle is easy to solve. The key to receiving the signal is not the power of the radio, but a combination of 3 other things. First, there must be very large antennas. Second, there must be directional antennas pointing at each other. And third, we need radio frequencies without tons of human-made interference. The antennas the Voyager space probes use are indeed very big. Have you ever seen satellite dish antennas some people have in their yards? They're typically 6 to 10 feet in diameter. Well, the Voyager spacecraft has an antenna which is 12 feet in diameter. And it transmits to large antennas on our planet. Earth antennas and the Voyager antenna are pointed right at each other. The centers for receiving signals from Voyagers located on our planet are positioned at an angle of 120 degrees to each other. This allows them to provide Voyager 1 coverage at any time of the day, no matter what Earth's position is in relation to the spacecraft. These receiving stations are situated in Australia, Deep Space Network Station in Canberra, the USA, and Spain. Let's try to figure out how communication works on Voyager 1. To do so, we need to discuss the design features of the space probe's radio reception equipment and the computer system serving it. We'll start with AASC, which stands for the Articulation and Control Relationship System. Its main purpose is to send data about Voyager's position in space and its route back to Earth. High-gain AASC antenna is always directed toward Earth to help amplify the weak signal. By the way, once it broke down, but specialists repaired it by updating the program. Voyager's signal strength keeps decreasing, causing the data rate from the spacecraft to Earth to decrease too. In 2017, for example, the probe's signal strength was many, many times weaker than the signal of a conventional FM receiver. Luckily, modern technology has seriously improved the sensitivity of the receiving antenna network. The increase in signal gain is achieved by capturing the signal from Voyager by a station on Earth to provide stable communication between the probe and Earth. The wave frequency should equal 2114 MHz. As for reverse communication from our planet to Voyager, it occurs when the space probe receivers are synchronized with the frequency of the uplink carrier biphase. The probe converts it into a two-way downlink carrier signal and sends it back to Earth. Not so long ago, NASA announced that Voyager 1 had started experiencing problems with determining its position in space. The data the spacecraft was sending to Earth had nothing to do with its estimated trajectory and flight speed, but specialists at NASA managed to figure out where the failure was. The AASC had started sending data through an onboard computer that had stopped working years before. It was this computer that had been corrupting the information. Once experts realized what the issue was, they commanded the AACS to resume sending data to the right computer. At the moment, Voyager 1 seems to be still traveling along its initial path, which is indirectly indicated by the stability of the radio signal emitted by the probe. Speaking of Voyager's journey, gravity assists their maneuvers. When they were launched, all the giant planets were conveniently located in a relatively narrow region of the solar system, and the spacecraft managed to visit all of them at once. Both Voyagers are carrying time capsules intended for any intelligent extraterrestrial civilization. These capsules include greetings in 55 languages, as well as different sounds and images. By the way, Voyager 2 is now over 40 years old and is the most distant human-made object. And shockingly, scientists are still fixing its software issues.
The Earth might be on the verge of a huge change. Scientists have discovered that every 200 million years, comets start raining down on our planet. This comet shower changes how the Earth looks, reshapes the continents, and increases geological activity everywhere. We are in the 20th cycle, which means new transformations are coming soon. Why does Earth have active plate tectonics and continents, unlike any other planet? To learn the truth, geologists decided to check out zircon crystals. We often find these tiny crystals in rock. They're very tough and can survive crazy geological processes that could destroy most other minerals. But they're cool because we can use them to learn how old their rocks are. These crystals have some uranium in them, and it decays into lead over time. By measuring how much uranium decayed in a crystal and how much is left, you can figure out the age of a mineral. So, we can use this trick to learn a lot about the Earth's crust and history. Recently, geologists checked out zircon crystals from two of the Earth's oldest continents and regions, the North American Craton in Greenland and the Pilbara Craton in Western Australia. It turned out that rocks from these continents could tell us what happened to our planet during the Archean Eon, from 2.8 to 3.8 billion years ago. It was a crazy era for our planet, back when magma, rich in elements we've never seen before, pierced the surface and broke out for the first time. This event changed what the land looked like forever. And when scientists studied them, they noticed something else. It looks like there's a cycle where every 200 million years, the Earth starts forming new continental crust for some reason. When they explored this further, they suddenly realized that this might be because of our galaxy. Our solar system is located in the Milky Way galaxy, right here in the Orion Arm. An arm is a place that has tons of stars, gas, and dust. There are many of them in the Milky Way, bigger and smaller ones. and they extend and wind outward, making galaxies look like spirals. We're located in a minor arm, about 27,000 light-years away from the heart of the Milky Way, a horrifying black hole called Sagittarius A star. But our solar system doesn't just stay in one place. It moves at a breakneck speed of 150 miles per second. That's like crossing the Earth 22 times in an hour. Just like planets move around the Sun, the solar system rotates around the center of our galaxy. This orbital period is called one galactic year. Objects that are closer to Sagittarius A star move faster. You know, your typical inner lane advantage. But large arms, the ones that are further away from us, are much slower. They move at a speed of about 130 miles per second. That's just some 19 runs around the equator in an hour. Because of this difference, the solar system moves kinda in and out of the galaxy's spiral arms. This is like when fans make a wave in a stadium. This leaves a mark on both the solar system and our planet. There is a vast, distant region around our solar system called the Oort cloud. It's about 4.6 trillion miles away from the Sun, like traveling to the Sun and back 50,000 times. Now, the Oort cloud is filled with comets. You might not know this, but they're way more dangerous to us than regular asteroids. Asteroids come in different sizes and are usually just rocks with some metals. They don't have a glowing gas around them. They just vibe around the Sun in their main asteroid belt, somewhere between Mars and Jupiter. And if the almighty Jupiter with its crazy gravity doesn't stop them, sometimes they come down on us, causing some havoc here and there. But a comet is a small object made mostly of ice and rock. When it gets close to the Sun, it heats up and releases dust and gas. This forms a glowing cloud around it called a coma. This is what we see as a tail as the comet moves, and their consequences are much more extreme. When we complete one galactic year, the icy objects from the Oort cloud are pushed towards all our planets. And when we enter the big spiral arms of our galaxy, the rainstorm begins. Comets are much faster than asteroids. When they hit Earth, they leave huge impacts and leave giant craters. The energy from these impacts can melt huge parts of Earth's crust and mantle. The molten rock then rises to the surface, floating there. As it cools, it solidifies and forms a new crust. Over time, these small pieces of crust can merge and grow larger as more solidified magma attaches to them. Eventually, all this forms big continents. So, once in a galactic year, when comets start hitting Earth more often, they really change the Earth's structure and help create new land masses. Another proof of this is spheroidal beds. This is what we call tiny round particles created by material thrown out during impacts. When we look at them, they also match the cycle timing. Spheroidal beds on our planets formed exactly when the Earth was crossing the Milky Way's spiral arms, and most of them formed when it was just over 1 billion years old. There are many cycles that influence our planet. For example, the Milankovitch cycles, the ones that tell us how the Earth's orbit and tilt change over time. This affects the planet's climate, but this new 200 million year cycle is a whole new level. We used to believe that continents only formed because of things that happened deep within our planet. And, well, maybe asteroids influence it a little. But now it seems like the continents were born and shaped thanks to the Milky Way itself. Scientists now want to study these ancient deposits to see if it's actually true. If it is, it could mean that we're getting closer to some huge geological activity. The continents might start reshaping again, or even coming together to form a new supercontinent. The continents on our planet look like puzzle pieces that fit very well, like South America and Africa. And that's not a coincidence. Many years ago, they formed one supercontinent called Pangaea. Pangaea used to be a landmass full of unique creatures, like the giraffe-necked Tanystropheus, the toothless Lystrosaurus, and the reptile bird Drepanosaurus. But the ground beneath us is always moving, floating on magma like vegetables flowing on a super hot soup. And eventually, Pangaea broke apart. However, it wasn't the only supercontinent in our history. This coming together and then breaking apart happens pretty regularly, like with some toxic people. Usually it happens every 200 to 600 million years. So yes, all our current continents will come together again one day. We call it Pangaea Proxima, Pangaea Ultima, or simply Amasya. It could form during the next galactic year. There are many theories about how it might happen. Africa might merge with Europe, and Australia might move north towards Asia. Life on Pangaea 2.0 would be challenging. People would likely have dark skin, hair, and eyes. We would all hang out near the equator and along the coasts because the weather would be nicer and calmer there. The center would be horrifying, hot and dry, filled with deserts. There would be a common language and shared traditions. In general, such an event would really bring us closer together. No pun intended. However, it would also mean that if someone starts fighting, we're all screwed. Also, all the potential health issues might influence everyone on the continent. And let's pray that there won't be any large asteroids this time, or we're definitely doomed. This, of course, the movement of the Earth's crust will lead to a lot of cataclysms. But maybe humans won't even live on Earth by that time. Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal poor star. It suggests that the star that collapsed and formed BH3 was metal poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course. The size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll, Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.